Good morning, everyone. It's my pleasure to speak at the second international workshop on numerical simulation method for large deformation problem in geotechnical engineering. I'm Steve Sun. I'm an associate professor at Columbia University. And today I would like to talk about a finite micro-rotation material method for capturing the contact mechanics of micropolar materials. This work is actually primarily done by our associate research scientist, Dr. Wang Ma, in my research group. Before I get into the details, I think a lot of our audience are already very familiar with the material point method. But one of the important thing we would like to address is how do we extend the material point method initially for large deformations contained that coexist contained to a higher order micropolar problem. So micropolar material are actually material that have inherent internal structure, and that internal structure introduce size effect. So in the specific case of micropolar rotations, we would not only consider every higher order, every other type of higher order kinematics, but we will consider the micro rotations of the material. And this could be helpful in capturing strength localizations where the internal physical length scale can provide a regularization problem. And the material point and the micropolar method are actually a good match to each other because the material point can help us overcome the significant change of the topology due to the onset of shear bank, and in some case, even modeling a free surface problem for fluid mechanics without concerning about the mesh distortions or the need for remeshings purely due to the mesh quality deteriorate due to the large deformations. So a brief review of the micropolar theory. Our micropolar material are actually one type of higher order continuum where the micro rotations are actually considered significant enough to be captured in the kinematic. So in this case, a material point does not only describe by the position vector, but also by the director. So in 3D, you can consider a high or a low, a classical material point is simply a point with no orientations, but a micropolar material point would have a director or orientations. And when we measure the difference between the 2 points, that in the classical continuum case, we would actually lead to a Euclidean distance between the 2 points, basically the length. But in the micropolar material, because it has orientations, we also need to consider the curvature or the micro rotations that capture the in a different point the different orientations of the material. Here in the material point method, we need to overcome or extend the current material point method to actually cover this kinetic feature. So I will talk about the particle to grid and grid to particle projections that are specialized for the material point calculations, the convections and the micro rotation integrations. And then after that, the conservations of moment of inertia and angular momentum that we need to incorporate into the residuals of the material point method. And I would also show a few numerical examples to illustrate why micropolar regularization could be helpful and important for problems that involve a granular material and other type of geomaterial that have internal structure. So again, one of the way to think about micropolar material is that it's not necessary in that micropolar theory, a point is actually not necessarily exactly represent a point with no volume, but it can actually consider it as a point that represent a subdomain with some finite characteristic. And in that sense, the material point would actually represent the additional degree of freedoms would allow us to represent some kinetic and kinetic feature of the underlying microstructure. And the more general way to represent higher kinematic is to model it as a micromorphic material problem. But in micropolar material model, we are focused on the rotation, curvature, and the moment of inertia of the director that are actually for each material point. And the micropolar theory is actually very well established. It starts from in the 1919 from the Kosarik brother, and one of the we can find applications in modeling the microstructure using the micropolar theory in polycrystal material, metamaterial, and granular material, and also for clay with internal structure, I mean particularly in the mesoscale. So here we will consider a finite string kinematic. So as we mentioned before, if in the general case of the Cauchy continuum, what we actually need to consider is only the deformation mapping. Our strength measure are actually coming from the deformation gradient or other or some variations of strength measure that are based on the deformation gradient, which is essentially the gradient of the deformation mapping that help us map a reference body to a deformed configurations. The new thing that require us to add a new degree of freedom to represent the microstructure is the second one, the microrotation field. The microrotation field is actually a rotations. Rotation is in the special orthogonal group. So what it actually tell is to allow the director D to be rotated in the reference configurations. So for a point, I would let me use the three orthogonal base to represent the orientations. So a mapping of the material of the deformation map put one point into another point, but microrotation field is actually combined with the deformations allow us to map the reference and the current configuration from this into different orientation that also involve rotations. Okay, so the director, you can think about it as an additional coordinate for the deformation of just like the position vector. However, the director itself is orientations, and then it have to obey a specific property. If you recall what we learned from the rigid body dynamics or from the undergraduate course, rotations for in particular cannot be added together. So two rotation one, let's say R1 plus R2. If you add these two rotations together, it will be, you would discover that it introduces deformations. So in the large deformation kinematic, it requires specific treatment to actually deal with the revolutional law. In this case, we would actually parameterizing it in the axis angle parameterizations. Rotations could be represented by a procedural vector that gives us the spin, and then in that case, which is actually corresponding to the Lie algebra of the rotation tensor, and in that Lie algebra, the spin tensor is a skew symmetric tensor with three unknown in 3D, and that would actually consider a procedural vector that can be added together, or have a revolutionary law that are actually easier to deal with. We see that in the classical continuum mechanics, where the velocity gradient can be split into the rate of deformations and the spin term. That is actually for that very same reasons. Here we will use the exponential mapping to map the rotation tensor that are in the special orthogonal group into the corresponding Lie algebra. Now, another difference is the way the kinematics and the kinetic measure are actually occurred. Here we show the Lagrangian string tensor, and like the classical Cauchy's continuum, the green Lagrange string tensor is actually related to U minus I, the only identity tensor. The only difference is that U is no longer just the polar decompositions of the deformation gradient, but also related to the R head, which is actually related to the microrotations. And in order to describe the kinematic for the large deformation micropolar correctly, we also need the third order and the second order curvature tensor, which is related to the gradient of the rotations. Again, in the large deformation kinematic, the gradient itself also need to consider it carefully, because when we consider the mapping from the reference and the current configurations, we are actually switching the basis. So this need to be captured properly, and we will talk about the details in the next slide. So essentially, the implementation is not particularly difficult. We just need to be aware of the careful treatment of the microrotation field, making sure that it won't violate the the physical constraint or the property of the special orthogonal group. So we would have the balance of energy, which actually related to the energy conjugate between the coupled stress and the rate of change of the curvature, and then the micropolar first pellicle stress or the second pellicle stress corresponding to the rate of deformations. So here we have the balance law, and the first one is classical, the divergence of the force stress, which by the way is no longer symmetric, times the body force would be equals to the inertia momentum density. But we also have a new equation here, where the divergence of the coupled stress and the new quality that are related to the skew symmetric part of the force stress are actually balanced by the intrinsic angular momentum density. And there's a new body force term that are actually capturing the body force of the angular momentum. One thing that is actually important to remember, or actually important to capture, is that in the balance of linear momentum, the density and are actually a scalar. But in the balance of angular momentum equations, the moment of inertia are a second order tensor that actually that could, in a sense, represent the inertia that are due to the shape of the microstructure. Due to the microrotations, this shape would also this second order tensor also need to rotate accordingly properly in order for the to capture that angular momentum. So K is actually defined as the intrinsic angular momentum density due to the microrotations, and K dot is the rate of change of this intrinsic angular momentum density. And one of the important things that we need to consider is to rotate is that we must able to rotate the anisotropic moment of inertia properly. So you see that the rotations are applied to the left and right of the moment of inertia, and such that when we consider the rate of change of it, we actually need the spin tensor that are applied to the moment of inertia. Okay, so long story short, R dot is actually not Rn plus 1 minus Rn divided by delta t. So with these important recognitions, we can actually solve the NPM problem in large deformation and also finite rotations without losing the objectivity. So this is actually the continuum theory, but another important detail issues that we need to take care of is actually to avoid the artificial jump of the velocity. This could be easily solved by introducing B-Spline Shape functions that to avoid the cell crossing instability. So this is actually the position vector spanned by the classical shape function, linear shape function of the finite elements. The issue is that at the grid point, we may actually have a jump on a width discontinuity in the positions, and when we take the derivative of it, it leads to a velocity jump that are actually non-physical. This could be easily correct by actually introduce quadratic B-spline functions that give us the smooth transitions of the internal force and the velocity gradient, such that we can actually avoid the oscillations. So here we would actually write the shape functions at the material point in position X as a WIP. So I think that a lot of audience and the speaker are familiar with NPM, in particular, the requirement to actually project the physical property at the material point to the grid and from the grid to the particle. So just a quick review here. It is necessary that during the projections that we actually preserve the momentum. And for the linear case, we would actually require us to compute the linear momentum calculation both at the material point, but also to project it into the background mesh to compute the residual. After the residual is computed, we need to project it back into the material point to have the material point convections occur. So the linear part is actually classical. The new part is actually the rotations. Remember that in the micropolar theory, in addition to the XYZ coordinate system, we also have the director to represent the rotations. So here, the angular momentum, just like the linear momentum, also need to be preserved. And then we actually introduce that additional rotational part to preserve the angular momentum. And what we actually have is that in the material point, we actually have the moment of inertia and then the microgyrations vector or pseudo vector, and then we need to compute the microgyrations gradient that are actually incorporated into the particle in cell mapping from the material point to the background mesh. So this is actually the new part. So the procedure is actually done using a backward Euler time integrator with a conditional stability. We would actually solve a contact problem, and as a result, there's an additional contact force, both from that are actually coming from the tractions and also coming from the micropolar contact force, both for the balance of linear momentum and balance of angular momentum. Okay, so this is actually the update of the kinetic law. We will have the internal force, the revolutions of the motions of inertia that are actually the new term that are unique for the micropolar material point method, and then the contact. The discretized internal force is actually look like this. Is actually surprisingly not super complicated. Again, the difficulty here is to obtain the term of the gradient of the rotation part. So here I would like to talk a little bit about the treatment here. After we compute the residual, we need to have the convections of the particle properly. Basically, what it means is that we need to move the material point according to the velocity that are obtained from the background mesh update. So the position is actually very trivial. We know the velocity, we times it by delta t, and then we allow each material point to move accordingly. But in here, in each material point, we also have the orientations, and that orientation need to be updated. So given particle orients is actually represented by a rotation tensor that are spanned by 3 orthogonal bases, and then at time n, we need to apply another Q so that it can actually rotate it to get the new rotation orientations. So to update to obtain the orientation gradient, we need to consider two parts. One is that the gradient of the microrotation tensor on a fixed coordinate system, which is actually the first term. And the second and the third term are actually coming from the fact that we are dealing with a mapping from between the covariance and the contravariance. That lead to that two additional new terms that help us take account of the fact that due to the deformations, the configuration has changed, and then the director itself can be changed simply based on the coordinate system update, or due to the fact that the basis vector in the current configuration are different than the reference one. So with that, we can discretizing it, and then once we compute the gradient properly, we can obtain the new updated curvature based on the gradient of the rotations. Again, these complexity are simply because the rotations are actually are in the special orthogonal group, and then we need to deal with this properly. We did validate our numerical model. So this is actually coming from the paper from Arlington and also from Du Bois' work in 1991. Basically, we try to impose, we want to check whether we can obtain a micropolar wave that we actually impose a velocity and a microrotations at one layer, and then we want to calibrate whether the micropolar wave and the shear wave are actually propagate in the right speed and have the right dispersion number. This is actually the results, basically showing that we actually can calibrate with the analytical solutions that are actually derived from the Arlington's paper quite well. In this paper, in the second problem, we try to simulate the Soliton wave, and then we obtain the energy functional from this paper in Bummer. Basically, the elasticity energy, the hyperelasticity energy looks like this, 4 equations, and we actually can obtain the stress measure, both the force stress and the couple stress, by calculating the first derivative of this energy functional. So in this elasticity model, we have both the low order classical material parameter for the elasticity model, but also have a coupling between the elastic deformations and the microrotation. So the microrotation itself can change in the force stress and vice versa. And also the deformations may also cause microrotations. So that makes the calculations more complicated, but it also can help us replicate some of the constitutive nature of material with internal structure. So the setup is like what we show in the right-hand side. We have this paper have analytical solutions, and we try to because the width discontinuity is actually not easy to present in this paper, we simply using the right-hand side of the solutions and then check whether for the right coupling term, whether we can obtain the same profile for the micro rotations and displacement. And this is another example with a cantilever beam with the torsions. What we actually want to compare is the micropolar effect on the torsions deformations and how does it change the wave propagation pattern. So the left-hand side is a micropolar beam that actually have that at different point of the time, you can see the torsion wave actually propagate. And then the left-hand side is actually the cohesive continuum without any size effect. So we can see that observe the difference due to the internal length scale that are introduced by the microrotations. We also using this idea to model impact with penetrations problem. We introduce a damage model that actually have degradations on this elastic energy functional. Only the first term that are actually degraded, and then we are assuming that the term corresponding to the curvature are actually not damaged. And we want to see whether the internal length scale here would actually have an effect on the penetration problem. And we actually also simulate a contact problem. This is an interpenetration problem, and we use a master slave contact model. Basically, there's a two background mesh, one for the bullets, another one for the background material. And we try to detect the penetration and separations based on the momenta. And we actually, if the material is in contact, we apply the frictional contact response. And then we detect the normal directions based on the gradient of the velocity. Okay, so so with that, then we can also introduce a micropolar contact where the frictional coefficients is not necessary only corresponding to the tractions, the tangential and normal part of the tractions, but also due to the durations mismatch. This is actually two problems. We have the penetrations that are actually hit at vertical line, and then another one that hit in the vertical in the upward angle. And we can see the velocity difference between the micropolar and the non-micropolar effect. In this case, it's not particularly significant, but we can actually see also another case where the effect is more profound. Nevertheless, we can actually still observe the difference in the velocity. And this is actually the actual simulations. We did not actually model. We did not actually show the bullets. And we just simply show the damage after the material getting hit. The material point actually fried away. Another interesting applications of the micropolar material point is to model landslide or actually granular flow. In this case, we are actually simply model it as a micropolar fluid. Okay, so we have this governing law that are actually derived from Arlington, and then we actually implement it. The first term is actually really classical, so we won't necessarily need to repeat here. But then the new term is actually the micropolar rotational effect. Okay, so here we allow bulk modulus to be there. We did not intend to model the incompressible fluid, so only a linearly incompressible one. So lambda V is actually the bulk modulus, which I intend to be really high. And the stress, unlike the solid, is actually not triggered by the triggered by the derivative string. This second term is actually the viscous term is actually due to the A tensor, which is actually the compute as a difference between the gradient of the velocity and the spin of the and then the spin term. Okay, so with that, this is actually incorporating the size effect could be important for many problems just to get a more realistic simulations. But in this particular case, it's very important. We actually have a background that I have a monitor and we have a box full of soil here. And then at the bottom, there's a hole, and then we can see the discharge of the particle. In this particular case, we can clearly see that the size effect is actually very important. Imagine that if we actually try to discharge a particle that are bigger than a hole, that would be a jamming occur. But even without the jamming, the size of the particle would definitely affect the discharge rate. And this could not be described in the classical container mechanics, at least not easily. So this is actually the response. We're simply trying it for the material that actually have low length scale parameter, and then we try to increase the length scale parameter. As we can see that the effect of the length scale is actually profounded on the alpha ray. The alpha ray slow down as the length scale increase, which is actually quite easy to understand intrinsically. And the reason is that the inertia or the angular momentum change with the size in this particular case. So this is a simulations. We can see that the particle are getting discharged. It have really large deformations, and then the change of the topology, which indicate that it's really difficult to simulate such thing in conventional finite element. So this is the conclusions. We have a material pond method that are actually designed for large deformations problem that are with inherent length scale. We did not show a very complex constitutive response in this paper and in this work, but this is actually under development. We have shown potentially a few important applications for wave propagations for regularizing the dynamic fragmentation problem and for the interactions of the micropolar solid and the fluids. One of the important things that we are currently working on is to introduce the machine learning to develop the micropolar constitutive law. This is a separate effort that we probably would discuss later on if there's an update. And we also want to use the method, and I think this is one of the great potentials of the material pond method, and to some extent also the micropolar material pond method, is that we actually have the numerical tools of the PDE solver that allow us to introduce a Lagrangian constitutive law for both solid and fluid without worrying about the mesh distortions. This is tremendously important for geotechnical engineering problem that often involve fluidization, liquefactions, and landslide that allows large deformations, not only large deformations, but also topological change of the bodies. And the material pond can provide a very convenient way to handle those problems. So I think this is actually all I have. I hope you enjoyed the lecture. If you want, you can find more information from our research group web page. It's www.polmechanics.org. Thank you for your attention, and I hope you enjoy the talk. Thank you.